Thank you. So I was asked to give this talk, and I was not actually really heavily involved. I was not out in the field on these missions, but hopefully it gives me a little bit of an independent perspective on some of what's going on. And which is the arrow. The arrow doesn't do anything. The other, oh, the other keyboard? Okay. Thank you. Okay, so Southeast Aerosol. So this is a map using IMPROVE and STN network data of the particulate organic matter across the United States, a contour map. And so obviously the Southeast US is an appropriate place to look at aerosols. It's got, aside from some scattered spots in the west, it's got the highest regional loading of particulate organic matter across the United States. So I think that was one of the main motivations for the missions in the Southeast, and it's very appropriate. One thing I want to really emphasize here is that it's not all organic in the Southeast. Sulfate, which is sometimes thought of as a Northeast problem, actually extends pretty far into the Southeast. If you look at this map, there's more sulfate in northern Alabama than there is in New York, southern New York. And so the aerosol in the Southeast really has a large component from sulfate. There's a large temporal trend in the eastern United States, and this map shows shows the improved network trends as squares, and the trends in the MISR data over the same period. This is summers in red, and there's really, if you choose the color scale right, there's really excellent agreement, but it's not all in the choice of color scale, of course. The networks agree that there's a trend in the eastern United States, very little trend in the western United States, and it's very large. If you take this over a 10-year period, the aerosol optical depth decreased by over 0.1 in the eastern United States, and that means roughly 10% of all sunlight was taken from the diffuse column and put in the direct column in the last decade. It's a huge change in the southeastern United States in the character of the sunlight, and this is driven mostly by reductions in sulfate, as I'll show. So this is taking the improved sites in the southeast U.S. I'm excluding Florida, they're different. And these are rural sites, and if you exclude Florida, they're weighted a little bit up towards Tennessee, so you're a little bit up towards the northern part of the southeast. Black is total PM2.5, red is sulfate, and green is organic time 1.9. And in the 1990s, sulfate was larger than organics at these stations. Now they're comparable depending on where you are in the southeast. It might be 70-30 organics, or it might be 50-50. Basically, both are now important. They're comparable. The seasonal cycle used to be driven largely by sulfate, and its contributions from both anymore. Sulfate is hygroscopic. It's more hygroscopic than the organics. That means the percentage change in aerosol optical depth and radiative forcing is larger than the percentage change in mass. The bottom figure has the trend over the period as a function of month of the year, and I'm actually not sure if there's a seasonal cycle in there or not, but the reductions in sulfate have been around 30%, reductions in organic have been around 10%, and knowing that in the 1990s it was mostly sulfate, of course, that's all anthropogenic, so that wasn't there, 100 years ago, so there had to have been an increase sometime during the 20th century in the aerosol loading over the southeast U.S. from the sulfate. I'm going to step back, put a little bit of my own data in the overview talk. So if you reduce sulfate, you might expect to also reduce organosulfates. So with the PALMS instrument, we can measure one organosulfate, two of them actually, but this is IEPOX sulfate. One molecule accounts for about 1% of the aerosol mass in recent field missions. If you take our recent calibrations, and we didn't know about IEPOX sulfate in 1999, if you extrapolate, if you take the same calibration for the same instrument in 1999, it was about 3% of the aerosol mass with more aerosol mass back in 1999. And if you work this out, there were about a 2% change in aerosol mass driven from IEPOX sulfate alone, and that's actually a small but significant portion of the overall trend in organics is from this one molecule. And some portion of the organic trend may actually be from organosulfates. So there's also temporal trends in other species. Elemental carbon is also high in the southeast U.S. compared to the rest of the country. it has also decreased. And you can try to look at the reasons for this decrease by comparing it to potassium. So potassium is emitted by biomass burning. It's not emitted by diesel trucks. And I've excluded dust events, because dust has potassium, and looked at the correlation between elemental carbon and potassium for the early and late portions of this time period. You have essentially the same correlation, essentially the same average amount of potassium, but you have a vertical offset. And that's indicating to me that the reduction in elemental carbon, which is no surprise, is coming from a source other than biomass burning. The reason elemental carbon went down is because of probably controls on diesels rather than a change in biomass burning over the last, say, 20 years. The annual cycle, there's been comments made about the annual cycle in the literature, and you can see that if you look at the improved fine mass, the annual cycle peaks in the summer. If you look at the MISR optical depth, the annual cycle of optical depth peaks in the summer, but you have a much larger seasonal cycle. But when you compare optical depth to surface concentrations, you have to worry about boundary layer thickness. So I found some boundary layer thickness numbers in the literature from 1967. You take the improved curve and you scale it to the boundary layer thickness. You basically reproduce the satellite aerosol optical depth. This doesn't mean there's nothing else going on. I mean, it isn't the case that you have this step function in all the aerosols in the boundary layer, but it does mean you don't have to invoke any novel mechanisms to explain the satellite seasonal cycle and optical depth. Joost in particular asked me to say something about aerosols and the temperature trend in the southeast U.S. This is the temperature trend from the Hadley Center model, and there's been very little warming in the southeast U.S., and of course you can put this next to the map of particulate organic matter, and I think it's sometimes assumed that local forcing by aerosols leads to a local temperature change. Maybe people don't say that explicitly, but maybe in the motivation slide at the beginning of their proposal they say, well, there's this warming hole and there's all this organics, so let's go study it. And so I'm going to spend a few slides here talking about that. And I can talk about basically three explanations. One is no, the east-west temperature trend is totally random climate variability. Yes, the aerosols kept the east cool. And the third one is that it's not random variability, but it's not really the aerosols in the eastern U.S. It's radiative forcing somewhere else on the Earth, and it just so happened that in a sort of deterministic sense, the east was cooler. And I'm going to show that I'm not a global climate modeler, and I'm not completely sure of the answer, but let me show you some of what's in the literature here. So this is sort of, figure is taken from this paper by Wang et al. Talking about climate trends over the United States. And it, I would say, is support for the internal variability. So the black is the temperature difference between the eastern and western United States, or the trend in it. And the colors are various ensemble metal members from a model, and the data and the actual temperature trend is within the variability from ensemble members of the model, indicating that you probably can explain it from internal variability. And then there's some other papers talking about how the variability is driven by sea surface temperature patterns, which on one hand might be internal variability, or they might actually be sort of the global climate mode that I'm talking about in a minute. And here I'm going to contrast two very different model results. So in this paper by Mickley et al., they removed the aerosols from the eastern U.S., from all of the U.S., and got this forcing pattern, and then got this temperature response. So the temperature response in this case looks a lot like the forcing pattern. On the other hand, paper by Schindel et al., this is a global aerosol forcing, so they're not looking at specific regions, and this is the temperature response. And the temperature response doesn't really look like the pattern. In particular, you can see in the Arctic the sign's reversed. In the GISS model, they have positive radiative forcing from black carbon in the Arctic. And the temperature response is to cool, and that's because there's an Earth climate mode where the Arctic cools more than the rest of the planet, and that dominates over the local temperature effect in the temperature response. And there's sort of a similar pattern here in In this paper, Hill and Meng, this is actually looking at a geoengineering problem where they inserted aerosols into these 3 boxes to try to brighten clouds. And then, of course, you get, and this is the forcing that you get mostly in those boxes, but a little bit of it spills out to other places when you put the aerosols in. And then in the bottom figure, this is the response they got. And I would say if you hid this top figure and looked at the bottom figure only, you would not be able to find those 3 boxes very easily in the bottom figure. You know, in particular, you got this huge warming over Alaska where there's no forcing. Actually, I think by chance you have a east-west temperature contrast in the United States. I mean, it came up from somewhere else. And kind of the way I view it is that, and you also, interestingly, have an east-west across the Pacific. You have these climate modes like El Nino, Arctic cooling, things like that. They get excited by various patterns of temperature forcing. And in my mind, that's probably what dominates the response. So conclusions, I've run a little fast, but started a minute late, and maybe there'll be time for questions. One of them is don't forget about sulfate. And I would say we have a lot of new tools and a lot of excitement about organics. There's a lot of really interesting chemistry out there. We don't, in some ways, have the corresponding new tools for sulfate, and there's still a lot of unknowns. I mean, the gas phase SO2 plus OH is known, but the cloud water chemistry, we don't have a lot of new measurements of cloud water chemistry. And the models disagree wildly on the fraction of wet oxidation to dry oxidation of sulfate. And I did a little metric before this talk of looking at the rate at which papers are being published on organics, climate, and aerosol, and sulfate, climate, and aerosol, and so on, and then comparing it to the radiative forcing. And of course, there's more papers being published on organics, and the sulfate radiative forcing is much larger. So per radiative unit of radiative forcing, we're publishing 5 times as many papers on organics as sulfate. And you might say the uncertainty in organics is bigger, but that metric for organics is bigger than the one for black carbon, on which arguably the uncertainty is also very large. The Southeast US has changed a lot in the last 25 years. It's one of the larger decreases in the world. This is the global map from MISR of aerosol optical depth trends, and the United States Eastern stands out as a pretty big trend. And the aerosol is getting less acidic. It's already, if you look at STN network data, nearly neutralized in Atlanta and a lot of other places. It means there's going to be more nitrate in the future. There's already a lot of nitrate at nighttime and in the winter. And nitrate has very different behavior than sulfate and organics in terms of being sensitive to temperature and relative humidity and things that these other species are not. The boundary layer depth explains much of the seasonal cycle and optical depth. There's a poster by Nick Wagner right now, unfortunately, about little organic aerosol formation aloft. And I would say, in my opinion, don't assume that local temperature trends induce a local temperature response. Think more about in global patterns of temperature response. Thank you.
There's plenty of time for questions.
Dan,
Yeah.
I want to challenge your opinion.
Okay.
That, aerosol trends are not driving. Because if you look at the temperature trend with the U.S. in the past couple of decades, we've had a warming that far outpaces the warming for the rest of the world. And it's very, it's certainly very consistent with the trend in aerosol that has been observed.
But I would say you can look at other places in the world where you can certainly find other places where that's not the case. I mean, you could go probably to Alaska and get an opposite response. And to me, the way oceans and the atmosphere carry heat around, it's different. But I'm going to say, I hope that this will invite some discussion here among the modelers and people on this subject. And something that it actually may be very different over land than over ocean, how much local response you see. I don't know. It may be very different where in the world you are. So let's have some discussion after the between people.
One more?
I'm surprised by your boundary layer depth explanation. Most people describe these seasonal cycles and optical depth changes with humidity. And actually, most of the optical depth is coming from water, not from anything else from the water. If you make the boundary layer depth go up and down, it changes extinction, but it doesn't change the column interval versus the optical depth.
Well, it is a good point about relative humidity. Southeast U.S. is fairly humid through a large part of the year, but the next level is to take into account the relative humidity. And it does actually mean, when you have a deeper boundary layer and the same concentration at the surface, that there's actually more aerosol mass in the column. And that seems to be one of the dominant effects. And I'm not saying with that figure that that's the only thing going on, but you can't, but it is one of the dominant parts of the seasonal cycle, that the boundary layer is deeper in the summer. And that's sort of the first order explanation.